Okay,
Okay.
I think
Work.
I think it's working now, and assume that you can see the screen here. So the title is Diffusion Model for Stochastic Parameterization, a case example of numerical precipitation estimates. As you mentioned, I'm currently working at Chinese Academy of Science. Previously, I was working at Lawrence Livermore National Lab, like working on combining deep generative models and dynamical models to improve the forecast across weather to climate scale. And here I'm basically continuing what I have been doing in LNL. And previously I was trying something like a variational autoencoder and GANs, but now I think that there's a game changer coming. So I will tell you why. I always enjoy start a presentation with the following big picture, that is what we have achieved through the past 150 years in the field of climate studies. So all these things start from like the beginning of 18th century when we first collect use electric telegraph to collect weather data, and we extrapolate those data to give us some weather forecasts. And gradually, Birknes developed these equations that govern the atmospheric dynamics. And then Richardson said that maybe we can try to solve these equations by hand using numerical methods. So he did the first try, but did not success. And in 1945, von Neumann tried to solve these equations using the first electric computer called ENIAC. And Giuliani developed the so-called Chinese report telling us what we should do in the coming 70 years of this field. That is basically trying to develop more complicated models that include more different components, trying to describe different spheres of the climate system. And with the advancement of satellite remote sensing and the new computing techniques we have, we can now resolve the equations to a finer and finer resolution. And we also have different observations giving us the initial state. But we realize that it's a chaotic system and we don't know what will exactly happen in 15 days. But we still try to predict the climate, and we have the CMIP project. And I think there's a very fine picture here in the CMIP project that telling us the three key uncertainties in climate prediction. One is called systematic bias, which comes from the model we have, and the other is the representation to forcing, which tells us it's kind of aleatoric uncertainty. We don't know what will happen, how much greenhouse gas we will emit to the environment. So we don't know the exact future, the forcing. And the other is called variability, predictability. I think it comes from the chaotic nature of the climate system. That is, a very small initial state perturbation would give us a very different results in a very short period of time. So basically, I think climate science is trying to disentangle these three kind of uncertainties: model systematic bias, internal variability noise, and the forcing or the representation of the forcings. But I think we are kind of bottlenecked here as the models become more and more complicated, and the observations coming from different sources are trying to blur the way that how we can see clearly the exact picture of this system. So there's something called machine learning that come into play because we think that maybe our human intelligence is not enough for us to keep improving this complicated observation and simulation system. And there is a kind of like a buzzword called AI for science, and we use artificial intelligence or exactly machine learning to do science. We have the following things to do. One is to explore or control like different experiments, and the second is to fill in the missing parts or fill in the like coarse-grained things. And third is to do computation acceleration. Maybe we can use Fourier neural operator to accelerate the numerical models like what they did in NVIDIA, but now they use graph casting DeepMind to do weather forecast. And the fourth, maybe it's more straightforward, is to do inverse modeling. We have the DNA figure here. They have different forms. Once we get this kind of structure from this kind of a picture, we know that the DNA is like this, and they won the Nobel Prize. But for now, we just took pictures of all the structures and get their figure here, and then we can do the inverse modeling to see what kind of figure would result in this kind of structure. And we can do some kind of inverse modeling, try to calibrate the parameters or trying to like see what kind of scenario give rise to what kind of results. And the final thing is called automated scientific discovery. Actually, we have done it like 100 years ago. Whitehead and Russell, they developed this Principia Mathematica, trying to say that if we have all the principles, can we have all the mathematical results? But actually, we don't. But still, we can know we have a lot of endeavor that trying to push this way forward, like Stephen Wolfram's physics project. And also there's something called adversarial learning. I think is pretty promising. That is, we may have a game between a bias detector and a bias corrector and post them in a like adversarial game. I think you have a paper having similar idea published in Nature Machine Intelligence. But before that, we do have a paper published in James Journal of Advances in Model Learning Earth Systems. And we try to formulate the GCM bias corrector and GCM bias detector and bias corrector, these two players in a single game, and see if we can correct GCM biases in a systematical and automatical way. This is AR for science. And regarding climate science, we do have many existing applications. One is called inverse modeling, and we do know that climate models have a lot of parameterization schemes, and each parameterization scheme may have different parameters, and we don't know which parameter give us the best results. So usually we do weather reforecast or do climate forecast to infer how the parameters influence the outcome of the climate models. But this usually takes around 10 to the 5th power of running for these climate models, and we cannot afford that. So what we can do is that we just sample some parameters, and we can get their response surface. That is how these parameters influence the mean behavior of these models. And we build a surrogate model trying to emulate how these parameters influence the model results. And we can use standard Markov chain Monte Carlo to sample all those parameters, which is pretty fast. And the second is to do parameterization. We know that climate models are not fine enough to resolve all the geophysical fluid processes. So what we do is that we have the resolved process as the input and put them into some semi-empirical functions to infer the impact of the unresolved processes on the resolved scales. And we have a lot of empirical equations, but it turns out that some data-driven solution might offer better results, like this kind of convection parameterization and this boundary layer parameterization. And the last thing is to accelerate the existing model, or try to replace them. Like we can do it using the transformer structure, digest the whole ERA5 data set, trying to see how the previous hours circulation field would give us would yield the next hour's circulation field, and we do it like using an autoregressive manner. Or if we do like more carefully, we can use this kind of icosahedral meshing to further discretize the geo field, and then use this kind of model to predict the weather. It can be pretty fast. And the last is about nowcasting. We know that the reason why we cannot do really good forecast is that we do not have a good initial state estimate, and second, we do not have a very good model. But if we just take into input of the radar reflection images and we put them to predict the next few hours precipitation, it turns out that we can achieve the best result here. So that's what we do here. But I think most of these things are like using a supervised learning manner, or if it's science, we know that we usually say that it's a control experiment. We have a well-developed experiment where we want to know how one factor influences the other factor. So it's called supervised learning. We can take into input of the predictor and try to infer the results of the predicand. But I think that for climate science, it's a chaotic system. It's very high dimensional. Usually we cannot design such good control experiments, which means that we don't have a good environment telling us how one factor exactly influences the other factor without changing all the other factors. So I think this formula might give us a better, allow us to better apply data-driven models or to use machine learning. This is called probabilistic machine learning. That is to use machine learning or exactly deep learning tools to estimate some unknown probability distributions. And here, if we recall these three uncertainties in climate science, that is model systematical bias, and forcing, the other is the internal variability noise, we can put them into this single framework that is for different models, or we take reality as another model. There is something that we care about and how they influence the predictant. And we get all those data from different sources, like from simulations or from different scenarios, and infer how one predictor influences the predictant. And we have a learning machine. The learning machine is denoted as capital theta. It can be a deep neural network. It can be a diffusion model. It can be a transformer. And theta is the parameter that we need to learn. And in this way, we can know, we can digest all these different data and apply powerful deep neural networks to get something that we want. And the resulting entropy of this probability is the internal variability noise that is left after we control X here. And I think this formulation, although very simple, can serve as a foundation model in climate machine learning, just like the stable diffusion model you did into input all the images, and then giving a style, giving some text description, you can get the results of that. You can sample some image of that. And with this, we can see that for different climate models, for different forcing scenario, for different initial state, we want to know the distribution of the rest. So if we have a single model that take into input of all the CMIP6 dataset, maybe we can know a lot more about what they seek here. That is the forcing, the internal variability noise, and the model systematical bias. So that's a kind of a big dream. And I don't think it can be true before this year, because it has a lot of requirements which I'll dissect soon. But I think maybe it could be possible in a very soon time. But before that, let's see something simpler. Let's see some classical machine learning applications in climate science. And then we find some classical models, and I will introduce the diffusion model. Maybe I don't need to introduce the diffusion model, but I want to introduce how we can apply it in some classical problems. So the first application about using machine learning in climate science is to do statistical downscaling. And here I'm referring to the task of inferring the unresolved precipitation process using the resolved geophysical fluid dynamics. We have been doing this for hundreds of years. First, we see the synoptic map, and we know that there is a cyclone here, so we know the characteristic precipitation pattern downside. This is called Bergen School cyclone model, which we learned it here in China, like in our middle school. But in dynamical models, we already have the numerical solver for this geophysical fluid dynamics. But the precipitation is represented by a series of parameterization schemes from cloud microphysics to convection. And what we did here is we crop out a synoptic scale map, and we have the companion precipitation field listed here. These are from observations or from some grid merged data set. And we have this convolution recurrent structure trying to take into input some useful inductive bias, like the circulation field are translational equivariant, and they're the state variable representing the state of the hydrogen materials, trying to infer precipitation. And we get really good results, like if we look at the correlation coefficient. And here are results for correlation coefficient at different resolutions for the continuous United States. And we can have a correlation around 0.74, which is kind of inspiring. But if you look at specific events like hurricane, you will see that it's like there's too blurry, and the results are hardly useful. And the other thing is about probabilistic forecast. Once we go beyond the weather scale, we have something like we have the chaotic effect would result us in a lot of different states that are, some of them are more possible, some of them are less possible. And we have these are these things frequently occur in sub-seasonal to seasonal forecast. And we can dissect the bias in sub-seasonal to seasonal forecast into these 4 factors. The first 2 are from the initialization. We may have we may not have the full picture of the initial state of the climate system, and if we use subcoupled ocean atmosphere models, we may have something called initialization shock. And when we run the model, we have the model formulation error. And when we do ensemble modeling, we have the insufficient sampling of forecast spread. This is called aleatoric uncertainty. This is called epistemic uncertainty. And if we want to apply machine learning to disentangle these 3 factors, what can we do? Well, we can do it like this here. We have X as the ocean heat content, D as the indicating which XY example pairs coming from which model. It may come from CESM or from GFDL model, but we just put them together and see if we can learn how different models differ in their way of how to encode the predictor, the probability dependency between X and Y. And we have, maybe preferably, we have a spherical convolutional neural network as our learning machine. And we dump all the CMIP 5, CMIP 6 models into this thing here and do maximum likelihood estimation. And once we get that, we may say that given the ocean heat content of the current year and given this model, what would its prediction look like? And the other model, what would its prediction look like? And if it's reality here, what would the future look like? So that's what we did. We try to put all this CMIP 5, CMIP 6 data into a single conditional generative model to make seasonal forecast. Actually, it's pretty good. And the third thing is to estimate the historical current climate state using limited data. We know that historical observations, they are not comprehensive because we do not have so well covered observation instruments. But it turns out that we can use something called partial convolution to get here from here, and it's really accurate. But 2 years ago, there's something called masked autoencoder. If they do not use convolutional structure here, they can learn the dependency between different places and recover the picture with like 10% of the information in this figure. And I think it's a good way to learn tidy connection or how one factor influences the other factor. But the drawback here is that this is still a deterministic model. And a member from my group is trying to develop this, to improve it to a probabilistic model, and to see that how two different locations are tightly connected, and how the knowledge of different locations might give us the knowledge of the whole picture. And I think it might be pretty useful in data assimilation tasks. And the other thing, as I mentioned, is that maybe we can try to see CMIP coupled model in the comparison project, which is here, like in the eye of a deep generative model. That is the foundation model idea. And the current CMIP, although they are pretty big already, they have 3 drawbacks. One is that they do not have sufficient sampling of internal climate variability noise, and they have ubiquitous model systematical biases, and they have insufficient exploration of possible emission scenarios. CMIP 5, they have 4 emission scenarios. CMIP 6, they have 6 to 8. In CMIP 7, can we have infinite many emission scenarios by doing interpolation between different emission scenarios? And we need fast generation of model ensembles, learn where model differs, and create representative emission scenarios. So if we consider all these 3 uncertainties together, maybe we can do it. But these have a really high requirement on the underlying probabilistic model. It's no longer trying to estimate the expectation of Y given X, but we want to know the probability distribution. And we know that this is a simple idea, but a simple but powerful idea. The difficulty is what should serve as this learning machine. Can we use the generative adversarial net to do this? And probably the first thing to do is to clarify what the learning machine should be like. So it should have the following 6. It should fulfill the following 6 requirements. The first is that it should have realistic samples, so that all the samples we fit in here can have realistic log probability, so we can maximize accurately. And the second is that we want to have full coverage of the PDF. We don't want to cover part of it and run the model like iteratively, so resulting in something that's totally unreasonable. We want the model to cover all the modes here. And it's not fitting a static probability distribution. It's not like stable diffusion. We have all the images there, and we do not need to care about the condition. But in climate science, usually we do is that we have a condition, and for each condition, usually we only have one single realized sample of it. And can we still learn a flexible control of this condition? And the fourth one is scale adaptability. It's particularly proposed for parameterization. So for example, we know that the two holy grails in developing data-driven or in developing parameterization schemes is uncertainty aware and scale awareness. So it should work for different scales, like from convection scale to synoptic scale. And can we just take into input of a larger picture and have the model automatically depict where it should care about? And that's what we want the model to do. And the fifth one is fast sampling. We can accomplish this with numerical methods. We just keep creating a lot more ensemble members of the dynamical models, but that's too slow. Maybe we can do it faster. And finally, we want to have accurate probability estimate. That's for a task of climate change detection. That is, if a single model here and D is a single model, the results coming from different emission scenarios. If we can know the exact difference between two probability distributions, where the only difference between these two distributions is the emission scenario from a dynamical model that creates these samples, then we know then we have a clear idea of how climate change influence the climatology influence the climatology. Here, the climatology is described by a very large dimensional probability distribution. And so given this task, that I always try to find the best model that we can use to march toward this goal. And what probabilistic learning machine should we favor? So there is a very classic tree for classifying different generative models, and part of them can fulfill part of these requirements, but no single one can fulfill all of them before this year, I would say. So in 2014 to 2022 is the era of generative adversarial nets and variational autoencoders. But since June of last year, there's a game changer here, and maybe it's the era of diffusion, because nowadays maybe we can fulfill all these requirements with a single model, and I will explain why. So I would try to describe and try to introduce the diffusion model in a very classical, very classical problem, still the problem of numerical precipitation estimation. I think to do downscaling or to do this kind of parameterization is the low-hanging fruit in climate machine learning. And if I'm not doing this, I believe someone else is doing it. And I know Stephen Rust might be doing it. I know Mike Pritchard might be doing it. So the problem formulation is as follows. We have the resolved dynamical field come from CFS reanalysis for the past 30 years. Is half degree hourly geopotential height, wind, humidity, temperature at different pressure levels. And we also take into input of the static input like the 0.1 degree elevation data. What we want to estimate is the underlying 0.1 degree 3-hour multi-source precipitation observation. So here is the study area, and here is the typhoon Lakima. Is the second largest typhoon that we have observed, and these are some snapshots of the precipitation in the hurricane center here. And here is trying to use UNet to estimate the precipitation, 3-hour multi-source precipitation from this half-degree hourly geopotential height, wind, humidity, and temperature. Those are the resolved dynamics. And we can get pretty good results regarding correlation and root mean square error. But as I mentioned, it's far from enough. And what we want to do is that given this kind of closely resolved geophysical fluid dynamics, can we know the probability distribution of the underlying fine-grained precipitation? And we hope to maximize the conditional likelihood of all the observations to give us the good model for estimating precipitation. And I will first introduce some baselines here. The first baseline, I think there's a paper published in James from Tim Palmer's group, and they're using, they compare the two baselines here. The first is conditional variational autoencoder. So if they try to learn this kind of conditional generative model, where X is the resolved geophysical fluid dynamics, Y is the precipitation observation, what they did is they dissect this log likelihood into these three components. The first two terms are called evidence lower bound, and the last term is the residual term. So what they did is they maximize this elbow term to implicitly push up this log likelihood term of the generative model, and is deeply rooted in the statistical learning theory. And what they did is that they have a prior distribution like standard Gaussian, and they have the distribution they want to approximate. So they try to find, so for each sample here, there should be a corresponding sample here that gives rise to this realized sample. And all the samples here should take the place of all the prior here. So these two terms basically like quantify these two requirements. So that's what convolutional variational autoencoder did. As you can see that we are learning two models at the same time, the encoder and the decoder. When we're trying to do sample, we just get some random seed here and put into the decoder. So hopefully we can get an unbiased sample here. And the other thing, which is kind of more popular, is called conditional GAN. So what GAN did is that they try to approximate a probability distribution by forming a two-player game. One is the discriminator, the other is the generator, and we try to generate try to approximate the distribution of all the cast images. So what we did is that we have a pseudo-random generator. It might generate like 100-dimensional standard Gaussian, and put this into a generator. The generator will give something that does not look like a cat at all, and we'll have a cat here from the true data set. The discriminator trying to say if it's true or fake. Then the discriminator says that, well, definitely this is fake, and the gradient here will be reversely used by this generator, so we can make this a little bit better. And finally, we have we can turn this standard Gaussian into some like really good looking cat image set. And DeepMind apply this for the precipitation nowcasting problem. They have a like regularization term here, that is all the samples generated here, their mean should not be too different from the reality. And if we are familiar with the probabilistic forecast field, we know that this corresponds to the CRPS objective function. So those are the two baselines here. But how can we do a diffusion model? So what is a diffusion model? A diffusion model is kind of a new generative modeling approach. And what they did here is that they have a target distribution of Y. Y is some potentially high dimensional random variable that we have a lot of samples. And we want to approximate its probability distribution. So what we do here is that we develop this diffusion function. So they are all the sequential of latent variables, where we have the alpha t and sigma t telling us how for different time the z should be like. So alpha t is a monotonically decreasing function of time. Sigma t is a monotonically increasing function of time. And at time 0, alpha t equals 0, sigma t equal, at time 0, alpha t equals 1, sigma t equals 0. So we have the original samples. Here I'm using the MNIST as an example. And at time 1, alpha t equals to 1, alpha t equals to 0, sigma t equals to 1. So we have standard Gaussian samples. And we can have this sequential of latent variable that drift y into some standard Gaussian. And we can dissect the log probability of y into this formula. Is really similar to variational autoencoder. And if we have alpha 1 equals 1, alpha 0 equals 1, alpha 1 equals 0, and sigma t is the same thing. So we know that this one is 0, this one is 0. So all we need to do is to minimize this one. And we have an analytical form for this thing. And we have a neural network parameterization term for this thing. So what we did is that we now have this thing as an analytical form. And we can do standard stochastic gradient descent to lower this one, so to maximize this one. And after this, we plug all the learned neural networks to go from standard Gaussian step by step to the original samples here. So that's diffusion model. And we can have different perspectives to describe this model. One is to estimate the gradient of the log likelihood, also called the skull function. Why do we estimate the skull function instead of just directly maximize this equation? That is, if we use a single neural network to approximate this one, then we have a regularization thing. That is, if we integrate over all the potential state of y, it should equal to 1. But that greatly lowers the expressiveness of deep neural networks. If we just approximate the gradient of the log likelihood, we can still push this upward. And meanwhile, we are not constrained by this like integration regularization anymore. And we cannot do it directly because in high dimensional space, usually most of the spaces there is no data there. So we do not know the exact gradient of this log likelihood. And we can add noise. So after adding noise, after changing all these score estimators, we can have a same thing like here. And Yang unified these two perspectives using the stochastic differential equation perspective. That is, we have a target probability distribution. We, like this typhoon here, we drift it toward white noise. And for every SDE here, there is a reverse SDE. The only thing you need to do is to estimate the skull function, which we can use the Fisher divergence or like something like it here to estimate the gradient. And then we can use standard SDE solvers to get us to go from the standard Gaussian to the random variable distribution here. So those are the three perspectives. So how can we implement this model? It actually turns out to be pretty simple. And the power is to repeatedly apply a neural network to estimate the gradient of the log likelihood of the target distribution. And after we train all these models, we chain them together to have so that we can go from standard Gaussian to the target distribution. And the neural network is a time-dependent unit. We have a target random variable sample, and we add noise to it to come to arbitrary time step, and we try to recover the noise. And we encode time in this manner, which is recommended in Yang's paper. And we calculate the Fisher divergence. So for all those steps, after we do all the training, like takes, I think, around 10 days for our problem here, we can get the probability distribution, like probability of y. If we want to get the probability distribution of py given x, where x is the resolved geophysical fluid, we use the control net idea. And the control net is to attack the condition here using a zero convolution manner to attach to these noisified samples. At the very beginning, it does not take any effect, but after training, it will learn how this condition influence the final distribution. So we get py given x. And as we are estimating the score function of this model, we can flexibly add the strength of the condition. If we use Bayes rule to dissect this equation, x given y, you know that it's a gradient of py log py given x plus gradient of log px. So we can flexibly control the condition strength. And here are some samples. This one comes from variational autoencoder. This one comes from GAN. And we see that there are a lot of very good looking samples, but it interpolates something that we cannot recognize. And here is a sample from diffusion. And here is sample from reality. So we can hardly distinguish the samples here and samples here. Some samples from GAN is good, but not all of them are perfect. This is about sample quality. And about sample distribution coverage, we can use similar idea of how we rank different generative models. And if we generate all these figures here, and we try to have a pre-trained classifier to tell if it's 0, 1, 2, 3, or 9, then we can have a class label for them. And we generate like 10,000 samples and see how many is 1, how many is 0. So we get this distribution. And we can see that the raw sample distribution and the diffusion generated sample distribution, they are pretty similar. While for VE and again, they have something called mode collapse. That is, they overestimate the samples for part of the modes while underestimate models. And here I'm showing the results for using diffusion models to estimate precipitation. And here is for the whole field. We can generate ensemble predictions for precipitation, like using VE, GAN, and diffusion. And we have different ensemble members. We can increase the member from 1 to 46 to 64. And we have a single parameter helping us guide how the predictor influences the predictant. And this is evaluated as 0.1 degree, and this is upgrading it to like 8 degree.
Baojiang,
and a very
can I ask a question?
Yeah, sure.
Sorry for interrupting you. Just can you remind me again what the exact setup here is? So you take, is it like what you showed in the very beginning, where you take a bunch of basically GCM variables,
Yeah.
and then it's this one. Yeah, okay.
Yeah, it's here. So the problem setup is as follows. We know that the GCMs can very well resolve the geopotential height, wind, humidity, and temperature at different pressure levels. And we know that their precipitation is not good. So we have the reanalysis geopotential height, wind, humidity, temperature at different pressure levels as our input. And given this input, we want to have a generative model telling us what would the underlying precipitation field look like. And it's a conditional generative model. That is, given same input, we want to know the distribution of this underlying precipitation. And this can be taken as a single sample that is realized by Mother Nature. But we know that if it's just half degree geophysical fluid dynamics, the underlying precipitation might not be unique. Of course, because we do not know the whole the fine picture.
Yeah, of course.
And what we did is that we have a sliding window here, trying to take samples. And this sliding window would get the geophysical fluid dynamical field and get the corresponding precipitation underlying it, and trying to maximize the Fisher divergence. So after we do this,
but this is sort of within one time step, right?
Within one time step, there is no prediction here.
Yeah.
But you can always use the predicted geopotential height as forcing to and then use this model to give you some predictions.
Yeah, basically. Cool. Great. Thank you.
Okay. So, and what we are evaluating here is that we have a test period where the model has never seen this data before. And the model takes into input of all the result field and try to generate, for each result field, generate 64 samples, 64 ensemble members. And we calculate the correlation coefficient and root square error scale of these models, like with different conditioning strengths for this diffusion model. And here is the average correlation coefficient. And here is at 8 degree. The black line is a UNet result. So UNet is like trying to do deterministic forecast. We know that it should do good at the resolution that is trained on. But if you look at here, our model far surpass the CNN the UNet model regarding a deterministic scale. So this is pretty worth celebrating, which means that even if you are you train the model on 0.1 degree, if you upscale these predictions, this is the only model that can surpass UNet. And this is a general scale evaluation, but I'm showing you something more interesting here. Is I show you the typhoon Lakima here. And we all know that is the trajectory is here. I take 10 snapshots, and those are the 9 of them. And you see that it's pretty extreme precipitation with a characteristic typhoon structure here. And if we have the resolve dynamics as the input here, those are observations. And we take into input of the resolve dynamics and take them into a diffusion model. And we get this kind of precipitation estimation results. And if you use the method developed by DeepMind, their precipitation nowcast paper, although they are doing nowcasting, you can use them for downscaling, taking into input of the same input that we have here and try to estimate the underlying precipitation. You get it here. It looks like it has scattered results, but you cannot capture the whole structure. Maybe it's because the model structure that we are using is a convolutional neural network. But I think that if you want to have this to produce this kind of well-organized structure, you need to have some sequential generating process, which is only diffusion model now has it. It's like cellular automata. You keep applying a theme or similar rules to a single pattern, and you get the whole picture. And diffusion is like a trainable cellular automata here, and it get very good results. This is a single sample, and this is for GAN. This is for VAE. VAE is a good, theoretically very good model, but in reality, if you try to train the decoder and the encoder together, and you try to sample using the decoder, you get this kind of blurry results, just like UNet. And UNet severely underestimates the precipitation, while the diffusion model shows currently the best results. We do have the wolf simulation for this particular case, but I don't have time to put it here. And the diffusion model generates much better details compared to wolf. If you configure the wolf to like 3 kilometer or even 10 kilometer resolution. And here is where I'm showing all the samples, all the 20 samples generated for each case. So for this case, you can see that these are our generated results, and this case are our generated results. And you can see that we are basically following all the patterns while giving a lot more diversity here. I haven't very carefully examined the probabilistic scale score of these models, but based on my experience, I think it's kind of a shock to get this kind of good results. I can see the patterns here, they are all there, and the extremes, they are all there. So basically that's all the results that I have for now. And I think a good in climate science, due to the high dimensionality and due to its chaotic nature, we should definitely turn to generative models or probabilistic models to make all the tasks that we used to do relying on dynamical modeling or supervised learning. And I think we can have, if we have a really good probabilistic model, we can do a lot of things. Like if we can accurately estimate the high dimensional data, a PX, then we can quantify what is climatology. Climatology is not about the mean state of the climate system. It's about every order of moments. And in climatology, we also mean that internal climate variability. If we can have a good generative model, maybe we can take use of all the existing climate simulations without running them again, without doing like such burdensome data analysis. And if we can have a really good high dimensional distribution estimation, we can have better data storage because the data structure informs us how we can compress those data. And we can benchmarking predictability. If we know the spread of a possible climate state and given observation of some initial state, we know if we are having some predictability. And if we can flexibly inject the conditions, we know maybe we can do better data simulation. So if we can inject the observations into the state estimation problem, or we can do probabilistic forecast, and we can do detection attribution. That is, we have Y as external forcing. Different external forcing may change the climatology. And we can do flexible domain adaptation. That is, if we change the model state, maybe we can have better models, or maybe we can do better climate change detection attribution and forcing climate sampling. So I would like to end with this picture here. And Van Octop have this fascinating tutorial about how to draw a horse. First, you draw 2 circles, you draw the legs, you draw the face, you draw the hair, and then you add more details. You get a horse. 4 to 5 used to be a joke because that people think that this is the most difficult part. But with stable diffusion, you see that 4 to 5 is no longer a joke. It's possible now because we don't even need a lot of pair data to get 5 from 4. And in developing climate models, first we have a simplified dicole that's trying to resolve a simplified version of the geophysical fluid dynamical equations. And then we have a full dicole, and we add parameterization. We add more parameterization. Nowadays, people are developing some concept called climate digital twin. I used to think that's a joke. That's a renaming of the existing technique. But with these probabilistic deep learning techniques, I think from 4 to 5 is a viable way. And I think it can benefit from the lesson we have in the left, 4 to 5, diffusion model. Maybe here, 4 to 5, we can also use diffusion model to do it. And here I just explained a very low hanging fruit of downscaling or super resolution of climate models. But if we recall the paper of like using adversarial learning to align the climatology of reality and simulation, the paper are published in James, and the paper, a similar idea published in Nature Machine Intelligence from your group. Maybe we can achieve much more in a much quicker pace. So that's my hope. And that's all for today. Here is a QR code for my YouTube channel. So you can see in my previous videos there. And here is the logo for my research group. We have the reality, we have the simulation, we have a Mobius band connecting them together. And I hope probabilistic deep learning is the channel here. Yeah, with that, I'm looking for questions.
Thank you very much, Baojiang. that was extremely interesting, and yeah, a very, very good fit to what we also have been thinking about and what we have been working on the last 1 or 2 years. I have a few questions, but maybe others start. Are there any questions?
Maybe I would have a question.
Oh, sure.
Yeah, thanks first of all for this really interesting talk. That was very inspiring. I was wondering sort of what the lead times is for the forecasts for which you show the results. Is it sort of in the weather forecast range, or is it more like short-term, medium range, or longer? I think I missed that.
There is no forecast here. It's just you have the geophysical fluid dynamic field here. Like you go past 3 hours, go forward 3 hours, and the current 3 hours you use this 9 hours to estimate the middle 3 hours precipitation. But you know that we have numerical weather prediction. They have pretty good geophysical fluid dynamical estimates for the coming 7 days. You can plug this model into these models, into the NWP models, and use them to generate precipitation. We have a paper published in 2019. We train a very simple convolutional recurrent neural network to estimate precipitation, and we use ECMWF subseasonal forecast to their result field to force the trend scene and get a precipitation estimate. So that one has better room square error and correlation to reality compared to their original precipitation forecast. And we even force a hydrological model using these 2 different sets of precipitation products, one from data driven and the other from like process driven. And we find that data driven shows a big advantage there.
Yeah, sorry, I was referring to the physical model, not the machine learning part. So this, I think you're using simulations from the CFS.
No, yeah, we are not using simulation here. We are using the reanalysis because we want to have paired data.
Okay. Yes. Okay. Yeah. Yes, that answers my.
Yeah, but we do have some students trying the nowcasting thing using diffusion model, and I think the results are pretty promising.
Mm-hmm.
And I know that many people are doing these things nowadays. The field is changing so fast.
Okay.
Yeah, I agree. It's very rapid. Baojang, about sort of turning this into forecasting, there's of course a certain error in the, let's say, I don't know, whatever your favorite forecasting system. If you take IFS, then of course, I mean, sort of we were suffering from this problem as well, that if you do forecasting, you take the climate variables and then, you know, like pressure and the relative humidity and so on. And then basically you do a final post-processing to get the precipitation.
Mm-hmm.
When ideally, of course, so this can only be as good as the predicted climate fields, like geopotential height and so on.
Yeah, exactly.
And they of course rely on the stochastic or whatever kind of precipitation and convection parameterizations that the model indeed uses.
Yeah.
So ideally, one would like to do exactly what you showed us, but not just as a final sort of offline post-processing, but to do this online in each step, right?
Exactly. That's why I call this a low-hanging fruit. I need to finish this as soon as possible.
We had the same situation.
Then, if I'm doing like online coupling, it might take another 1 year, and these things are no longer new at all. And I think this kind of paper would come out if it's not done by me, it's done by someone else, maybe in like 2 or 3 months.
Yeah, I agree.
Yeah, and I agree that to couple them with the dicot is the most difficult one, and I think maybe we do not need to follow what Mike Pritchard did. I mean, you might not want to develop a polarization scheme offline and then try to couple them back to the dicot you have the domain shift problem. They are not stable there, but you can always do it in an adversarial learning problem setup. That would be something huge. Do it. You couple it with the DICO, but you do not learn offline. You learn it online. That's the power of adversarial learning.
Yeah. Yeah. Okay. Great. We exactly agree on that. And maybe from your perspective, I mean, you showed us several examples, and like looking at the pictures, then it's sort of, I mean, the whole diffusion hype and these pictures that show that diffusion, the transformation of diffusion models work better than GANs. There's always sort of, I have a feeling, a bit of a selection bias here. Here it's clear.
Yeah.
That's your result. But what I would be interested in more, so I mean, it's very convincing. That's not my point. But from a fundamental perspective, how would you explain that diffusion models, and maybe, I mean, in particular spectral diffusion models, work better than GANs?
Okay, so the reason why GAN here is not so good is that we are using half-degree circulation field to estimate 0.1 degree precipitation. So if we use 0.1 degree circulation field to estimate 0.1 degree circulation, it would be much better than here. The condition information is offering too low information content to our final predictant. And that's why I'm not learning very well here, and it's not so stable. So GAN is not so stable. I can just train it like this, and maybe if you force me to train it again and again, I can get some better results. Here I'm just using it as a baseline. I'm not tuning it to a very deep level.
Yeah.
And the reason why I assume diffusion model is better, and actually is better, is that it's really like wolf. Let's see how we use dynamical downscaling to get a half-degree circulation field to 0.1 degree precipitation. We have a discretization of this half-degree circulation field using bilinear interpolation to get 0.1 degree initial field of wolf, and we run wolf. We update the state every few minutes